But that's expected, given Cassius's smaller aperture and the signal-to-noise requirements for detecting low surface brightness features. The primary mirror is only 13.5 cNES in diameter, about 300 times smaller in collecting area than Hubble's mirror, so it simply can't integrate enough photons to see the faint outer reaches of the coma. The brightness profile from Cassius is consistent with the Hubble measurements when you account for the change in distance and solar illumination. 3IATLAS was closer to the Sun during the Mars flyby than it was during the Hubble observations, so we'd expect the surface to be warmer, outgassing rates to be higher, the coma to be brighter and more extended. But there's no evidence in the Cassius data of a major outburst or dramatic change in activity level, which suggests that the object is evolving fairly smoothly as it approaches perihelion, rather than showing the kind of sporadic variability that some comets exhibit when subsurface ice pockets get exposed and suddenly start venting. The Mars Express high-resolution stereo camera also observed 3IATLAS, along with several spectrometers, a Megan spycam trying to measure the spectrum of light from the coma to identify what molecules are present. Those instruments are typically used to map the Martian surface, just a few hundred to a few thousand kilometers below the spacecraft, so pointing them at a target 30 million kilometers away. A target that's moving rapidly against the background stars required careful planning and precise execution. Whether they successfully acquired spectra with sufficient signal-to-noise for chemical analysis hasn't been publicly disclosed yet. Another casualty of the communication shutdown. China's Tianwen-1 orbiter and the UAE's Hope Mars mission were also supposed to attempt observations around the same time frame. The moderate-resolution imaging camera on Tianwen-1 and the Emirates Exploration Imager on Hope both have capabilities that could contribute useful data. Different wavelength coverage, different viewing geometries that might reveal features not visible to the ESA instruments. But no images from these missions have appeared in public archives yet either, and it's unclear whether that's due to data processing delays, decisions to keep results internal for now, or simply that the observations didn't yield anything scientifically interesting beyond what ESA already captured. The amateur astronomer community has been busy during this period, trying to fill the gap left by delayed professional releases. Simeon Schmaus, an astrophotographer with experience processing planetary, stack 20 frames from the Mastcam's camera on NASA's Perseverance rover, and reported finding a faint smudge at the location where 3IATLAS should have appeared in the Martian sky. The smudge is right at the detection threshold, barely distinguishable from noise, and there's legitimate debate about whether it's a genuine detection or just a statistical fluctuation that happens to fall in an interesting location. Mastcam Z wasn't designed to image faint comets. It's optimized for photographing rocks, soil samples, and nearby terrain features. So, pushing it to detect something as dim as 3IATLAS requires aggressive image processing that can introduce artifacts. The Perseverance images are publicly available in raw form, which is how Schmaus was able to access and process them even during the shutdown. NASA's policy of releasing raw image data as quickly as possible, sometimes within hours of downlink, is one of the genuinely valuable things the agency does for transparency and public engagement. It means that researchers and amateurs can work with the data without waiting for official processing and calibration, though they also take on the responsibility of handling all the instrumental corrections and noise reduction themselves, which requires significant expertise to do properly. The controversy around these amateur detections highlights a tension in modern astronomy between professional gatekeeping and democratic access to data. On one hand, you want trained experts with years of experience to be the ones making definitive claims about what has and hasn't been detected, to prevent premature or incorrect announcements that create confusion. On the other hand, confining analysis to a small credential elite means potentially missing insights that fresh eyes might spot, means slowing down the pace of discovery, and means reducing the diversity of perspectives brought to bear on complex problems. The 3IATLAS situation is exposing that tension more sharply than usual, because the stakes feel higher, because the public interest is intense, because the possibility of artificial origin makes every observation feel consequential in ways that routine asteroid tracking doesn't. Loeb's comments about the apparent media blackout need to be understood in this context. He's not claiming a grand conspiracy. He's highlighting a structural problem with how scientific information flows during government dysfunctions. If the high-res images exist and show something unremarkable, something entirely consistent with natural cometary behavior, withholding them serves no purpose and only fuels speculation that there's something to hide. If the images show something surprising, something that requires careful analysis before public release, that's more understandable, but still problematic, because delay gets interpreted as suppression regardless of actual intent. The optimal strategy from a transparency and trust perspective would be to release the raw data as quickly as possible and let the community collectively examine it. But institutional caution and risk aversion often prevent that kind of openness. The ESA images showing Phobos and Deimos in nearby fields, showing background stars, showing nothing obviously associated with 3IATLAS, except the primary fuzzy blob, are themselves interesting as null results. If there were a cluster of objects, if 3IATLAS had already started releasing mini probes, if it were fragmenting into multiple pieces, Cassis should have detected that, even at its limited resolution. The fact that it shows a single coherent source, no companions, no obvious debris field, argues against catastrophic breakup having occurred before the Mars flyby. It doesn't tell us what will happen at perihelion, doesn't constrain the mothership scenario definitively, but it does tell us that as of October 3rd, 3IATLAS was still holding together as a unified object. The faint features that ESA mentioned as possible noise artifacts deserve a scrutiny once the full analysis is published. Noise in CCD detectors isn't uniformly distributed. It has structure, patterns that can look vaguely like real astronomical sources if you're not careful about characterizing the instrumental background. Cosmic ray hits, hot pixels, red noise, dark current, all of these contribute statistical fluctuations that can occasionally mimic extended sources or point sources, depending on their spatial pattern. Distinguishing genuine signal from noise requires statistical rigor, comparing the putative detection against null hypothesis expectations, calculating false alarm probabilities, looking for temporal persistence across multiple frames. ESA's caution in labeling these features as likely artifacts rather than confirmed detections reflects appropriate scientific conservatism. The November reappearance of 3IATLAS from behind the Sun will provide another opportunity for both professional and amateur observers to assess its state if it emerges intact. If the brightness and coma structure are broadly consistent with pre-perihelion observations, scaled for the new distance and activity level, that would support a natural origin. If it emerges altered, if there are multiple objects where there was one before, if the outgassing pattern has changed dramatically, if there are new spectroscopic features indicating exposure of different materials, any of those outcomes would be significant and would demand explanation. The high-risk data, whenever it finally gets released, will provide a baseline for comparison, a high-resolution snapshot from October 3rd, against which post-perihelion observations can be measured to quantify exactly what changed and by how much. Chapter 7 Objects Around Atlas, Analyzing the Mars Orbiter Images. The question of what constitutes a detection versus an artifact is trickier than it might seem from outside the field of astronomical image processing. When you point a sensitive camera at a faint target millions of kilometers away, you're collecting photons that have traveled vast distances, photons that have been scattered and absorbed by dust, reflected by surfaces with complex geometries, mixed with background light from stars and cosmic rays, and instrumental noise. The resulting image is never a perfect representation of what's actually there. It's a convolution of the true scene with all the imperfections and limitations of your detection system, and teasing apart the signal from everything else requires careful statistical analysis. The Cassis images from ExoMars' Trace Gas Orbiter show 3IATLAS as the primary source, that fuzzy white dot moving downward near the center of the frame. In the animated sequence that ESA released, the background stars appear as streaks because the camera was tracking the comet, keeping it stationary in the field of view. While the stars moved relative to the detector during each 5-second exposure. That tracking is necessary to accumulate enough light from the comet without trailing it into an elongated blur. But it means that any other objects moving with similar angular velocity to 3IATLAS would also appear as points or small blobs rather than streaks. This is where the analysis gets detailed. If there were companion objects, mini probes, already released fragments from early breakup, they would be moving on trajectories close to, but not identical with, the main body. The exact motion depends on when and how they separated, what velocity they received during the release or fragmentation event, how solar radiation, pressure and gravity have affected them since small differences in trajectory accumulate over time and distance. So by October 3rd, any objects that separated weeks earlier would be displaced from the primary nucleus by measurable amounts, potentially several thousand kilometers, depending on their relative velocities. The Cassis pixel scale of 340 km/s means that objects would need to be separated by at least that distance to appear as distinct sources in the images. Closer spacing would result in blended light, a slightly elongated or asymmetric blob rather than clearly resolved components. The seeing conditions, the stability of the spacecraft pointing, the exposure time, all of these factors affect the effective resolution, sometimes making it better than the nominal pixel scale, sometimes making it worse. For Cassis observing 3IATLAS at 30 million km, the practical limit on detecting separate components is probably closer to 500 or 1,000 kilometers, conservatively. So, if companion objects exist and are separated by less than that threshold, they wouldn't show up as distinct sources in the Cassis images. They'd be there contributing to the overall brightness, potentially causing subtle asymmetries in the coma structure, but not individually resolvable. This is an important point, because it means the absence of detected companions in the Cassis data doesn't definitively rule out their existence. It only rules out companions that are sufficiently bright and sufficiently separated to exceed the detection and resolution limits of the instrument. The faint features that ESA's analysis team flagged as likely noise artifacts appear in some frames, but not others, which is actually diagnostic of their nature. Real astronomical sources are persistent. They show up consistently across multiple images taken minutes or hours apart, unless something catastrophic is happening to them. Noise artifacts, by contrast, are stochastic, appearing randomly as statistical fluctuations in the detector readout process. If a feature shows up in one 5-second exposure, but not in the next one taken a few minutes later, that's strong evidence it's not real. It's just a noise spike that happened to look vaguely source-like. The specific locations of these features matter too. Are they near the primary nucleus, where you might expect debris or ejected material? Are they strung out along the tail, where dust particles are being swept back by solar radiation? Or are they randomly distributed across the field of view with no particular relationship to 3IATLAS? The ESA analysis, when it's fully published, should include coordinates and brightness measurements for each of these features, allowing independent researchers to assess the claims and potentially identify alternative explanations. If there are any, Phobos and Deimos, Mars's two small moons, appear in some of the Cassis images as part of the background field. These are useful calibration sources because their positions and brightnesses are well known, allowing checks on the photometric accuracy and astrometric precision of the observations. If Cassis is correctly measuring the brightness of Phobos, if it's placing Deimos at the right coordinates relative to background stars. That validates the instrument's performance and increases confidence in measurements of 3IATLAS itself. Conversely, if there were significant errors or uncertainties in the Phobos and Deimos photometry positions, that would raise questions about the quality of the 3IATLAS data. Contemporary comets. Other solar system comets that happen to be visible from Mars orbit during early October provide another comparison set. How does 3IATLAS's brightness and coma structure compare to more conventional comets at similar distances from the Sun? Are the differences dramatic or subtle? Do they fall within the range of normal cometary diversity? Or do they represent something genuinely anomalous? The Cassis observations captured several known comets in nearby fields, allowing direct side-by-side comparison under identical observing conditions, which helps control for instrumental effects and atmospheric variations that might otherwise confound the analysis. The Mars Reconnaissance Orbiter's high-rise camera operates differently from Cassis in ways that affect what it can and can't detect. High-rise is a push-broom scanner, meaning it builds up images by taking narrow strips as the spacecraft moves along its orbit, stitching those strips together into a full frame. This design gives excellent spatial resolution, but requires a very precise knowledge of the spacecraft's motion and attitude to avoid distortions for a target like 3IATLAS that's moving against the background at a different angular rate than the Martian surface. The pointing and timing calculations become more complex, and there's greater risk of misregistration error that could blur or distort the image if HiRISE successfully imaged 3IATLAS. If the pointing was accurate enough to keep the comet in the detector's field of view throughout the exposure, the 30 km per pixel resolution should reveal whether the nucleus is a single coherent object or a contact binary, two lobes touching, or a rubble pile, a gravitationally bound collection of smaller pieces with gaps between them. The brightness distribution across the nucleus would constrain the albedo, the surface reflectivity, which in turn constrains the composition. Icy surfaces are brighter, rocky surfaces are darker. Metallic or manufactured surfaces might show unusual spectral properties or geometric patterns that natural materials don't produce. The lack of any verified companion objects in the datasets released so far from Cassis, from Mars Express, from any of the Mars orbiters, is a meaningful constraint, even though it's not definitive. It tells us that if 3IATLAS has released mini probes, they are either very small, below the detection threshold, or they're very dark with low albedo that makes them difficult to spot against the background sky, or they separated very recently so they're still close to the primary nucleus and blended with its brightness. All of these scenarios are possible, but each comes with its own implications and likelihood estimates. Very small probes, say less than 100 meters across, would be essentially undetectable at these distances with current instruments. They'd reflect too little sunlight, contribute too few photons to be distinguished from noise. But if they're that small, their capabilities are also limited. How much fuel can they carry? How sophisticated can their instruments be? How long can they operate before resources are exhausted? There are engineering limits on miniaturization, minimum sizes below which you simply can't fit all the necessary subsystems for a functional exploration probe. Very dark probes with albedo below 5% would be equally hard to detect. For comparison, fresh snow has an albedo around 90%. Typical rocks range from 10 to 30%, and the darkest known materials, like certain carbon-based compounds, can get below 1%. If the mini probes were deliberately designed for stealth, coated with absorptive materials to minimize their visibility, that would make sense from an operational security perspective, but would also suggest a level of paranoia or caution that might seem excessive, given that any civilization capable of interstellar travel is likely so far beyond our technological level that hiding from us would be unnecessary. Recent separation would keep the probes close to the main body during the October 3rd observations, within hundreds of kilometers rather than thousands or tens of thousands. In that case, we might see them in later observations, as they gradually drift farther from 3IATLAS, opening up enough angular separation to become individually resolvable. The November and December observations from Gemini, from other ground-based telescopes, from JUICE in late November, all of these would provide opportunities to detect companions that weren't visible during the Mars flyby, simply because geometric separation had increased enough to cross detection thresholds. The analysis here is about setting bounds, about constraining what's possible given the limits of our instruments and the characteristics of the observations we've collected so far. We can't prove there are no companion objects. That's effectively impossible to prove definitively, but we can say that if they exist, they must satisfy certain criteria about size, brightness, or separation distance, and those criteria narrow the parameter space, make certain scenarios more likely than others, guide future observations toward the most productive targets and strategies. The statistical approach that ESA is using to evaluate the faint features in their data is based on false alarm probability calculations. You define a detection threshold, a brightness level, above which you claim something is real rather than noise. And then you calculate how often random noise fluctuations would exceed that threshold purely by chance. If you set the threshold too low, you get lots of false positives, noise spikes that look like sources but aren't. If you set it too high, you miss real but faint sources, and reduce your sensitivity to genuine detections. The optimal threshold depends on the science goals, on whether you're more concerned about missing real signals or being fooled by fake ones. For 3IATLAS companion detection, the cost of a false positive is relatively low. You just report a detection that turns out not to be confirmed by subsequent observations, which is embarrassing but not catastrophic. The cost of a false negative, missing a real companion object because your threshold is too conservative, is higher because you might miss the key evidence that would definitely prove artificial origin or natural fragmentation. The ESA's decision to label the faint features as likely artifacts, rather than tentative detections, suggests they're prioritizing specificity over sensitivity. Better to miss a marginal signal than to claim a detection that doesn't hold up. The upcoming JUICE observations will use different instruments with different characteristics, providing an independent check on the companion object question. If JUICE sees features that correlate spatially with the faint signals in the CASIS images, that would elevate their status from likely artifacts to possible real sources deserving closer examination. If JUICE sees nothing unusual, just a single primary nucleus with normal cometry coma, that would reinforce the artifact interpretation and let us move on with higher confidence that there aren't large companions lurking near 3IATLAS. Chapter 8. November's Judgment Day. What JUICE will see. The Jupiter Icy Moons Explorer spacecraft is currently positioned in a region of space that most interplanetary probes never visit, close enough to the Sun that solar heating becomes a serious engineering challenge, using its high-gain antenna as an improvised heat shield, while relying on secondary antennas for communication back to Earth. This unusual configuration is a consequence of the mission's trajectory, the complex series of gravity assist maneuvers that will eventually deliver JUICE to Jupiter orbit in 2031, but for a brief window in November 2025. This inconvenient positioning becomes a unique opportunity. JUICE will have the best view of any spacecraft of 3IATLAS in its most active state, freshly heated by perihelion passage, potentially fragmenting or outgassing at maximum rate, potentially revealing characteristics that were masked or dormant at larger solar distances. The observation window runs from November 2nd through November 25th, 3.5 weeks of intermittent monitoring. As JUICE's orbital motion and communication requirements allow, the spacecraft will use multiple instruments: the Janus Visible Light Camera, the MAGIS imaging spectrometer for infrared observations, the UVS ultraviolet spectrograph, and the REM radar for any subsurface structure that might be detectable. Each instrument brings different capabilities, different sensitivity to various physical processes, different ways of probing what 3IATLAS is made of, and how it's responding to the post-perihelion environment. Janus can capture shape and surface features if the nucleus is large enough to be spatially resolved, which at the distances involved means detecting overall morphology, whether it's spherical or elongated or irregular, whether there are distinct bright and dark regions suggesting compositional heterogeneity. The camera won't resolve small-scale texture, won't see features smaller than hundreds of kilometers, but it should reveal the gross structure well enough to distinguish between a rubble pile and a solid body, between a single object and a close binary. MAGIS operates in the near to mid-infrared, where thermal emission from the warmed nucleus and reflected sunlight from the coma provide complementary information about temperature distribution and surface properties. Different materials have characteristic infrared spectra. Absorption features at specific wavelengths that act like fingerprints for identifying what molecules are present. Water ice has strong features near 3 microns. Carbon dioxide shows sharp bands at 4.3 microns. Silicate minerals have complex patterns in the 8 to 12 micron region. By comparing the observed spectrum to laboratory references, MAGIS can determine the relative abundances of different ice and minerals, track how those abundances change as volatiles sublimate away from the surface, watch the composition evolve in real time as solar heating penetrates deeper into the nucleus. The UVS ultraviolet spectrograph is particularly sensitive to certain atomic species and small molecules that fluoresce when excited by solar UV radiation. Oxygen from dissociated water, carbon from broken down CO and CO2 hydrogen from various sources. All of these show up as emission lines in the UV that are much weaker or absent in visible light. The relative intensities of these lines, their spatial distribution across the coma, the velocity information encoded in line widths and Doppler shifts, all of this feeds into models of how gas is being produced and transported away from the nucleus. If there are jets, localized regions of enhanced outgassing, the UV observations should reveal them as brightness enhancements or as symmetries in the emission line maps. RIME is more speculative in terms of what it might contribute. The radar is designed to penetrate ice shelves on Europa and Ganymede to map internal structure and search for subsurface water layers. Whether it can detect anything useful from 3IATLAS depends on the object's dielectric properties, its size, the signal strength after propagating millions of kilometers. If the nucleus is large and has significant internal structure, layering, or voids, or compositional contrasts, RIME might pick up echoes that reveal that structure. If it's small or homogeneous, or too far away for adequate signal to noise, RIME might see nothing. It's worth trying, though, because the information content of subsurface structure would be enormous, potentially distinguishing between natural aggregates and something more organized, more engineered. The critical advantage JUICE has over ground-based observatories is timing, while 3IATLAS is behind the sun from Earth's perspective. While terrestrial telescopes are blinded by solar glare, JUICE is on the sun-facing side, able to observe without that constraint. The geometry means JUICE will see the comet at its peak activity level, the days and weeks immediately after perihelion, when outgassing rates should be at maximum, when any thermal processes triggered by solar heating would be most evident. This is exactly when you'd want continuous monitoring to catch transient events. Sudden brightness changes, fragment releases. Anything that happens on timescales of hours or days, rather than weeks or months. The coordination with Europa Clipper's ultraviolet spectrograph is still being planned, still subject to mission scheduling constraints and resource availability. If it happens, If both spacecraft point their UV instruments at 3IATLAS simultaneously or near simultaneously, the two datasets can be compared to check for temporal variability, to verify that both instruments are seeing the same features, to use the different viewing geometries for stereoscopic reconstruction of the three-dimensional coma structure. The twin observations would also provide redundancy, protection against instrument failures or pointing errors that might compromise one dataset but not the other. The data downlink schedule is what pushes the results out to February 2026. JUICE is far from Earth, on the opposite side of the Sun during November, and the spacecraft's communication system is operating in a degraded mode, with the high-gain antenna unavailable. The medium-gain antenna has much lower bandwidth, meaning each observation generates more data than can be transmitted in real time. The data gets stored on board in solid-state recorders with finite capacity, waiting for better communication geometry in December and January, when transmission rates improve and the backlog can be cleared. Then there's processing time, calibration against instrument characteristics, and known systematic errors, preliminary analysis to identify the most interesting features before releasing anything publicly. So we wait. The observations happen in November. The data exists by late November, but we don't get to see the results until February at the earliest, possibly later if peer review or additional analysis takes longer than anticipated. This delayed gratification is standard in space science. Normal operating procedure for missions where communication constraints or data volume limitations prevent real-time release. But it's frustrating when public interest is high, and every week without new information feels like an eternity. The social media reaction to this timeline has been predictably impatient, with speculation running wild about what the delay might mean, whether negative results are being sat on, whether positive results are being carefully managed to avoid panic. The reality is almost certainly more mundane. Data processing takes time, especially for instruments that haven't been used in exactly this way before. Janus was designed to image icy moons at close range, not interstellar comets at millions of kilometers. Magus was optimized for surface composition mapping, not coma spectroscopy, adapting the standard processing pipelines to handle this unusual target, validating that the calibrations are correct, understanding the noise characteristics and systematic errors. All of this requires careful work by scientists who are also busy with a dozen other mission responsibilities. Rushing the analysis to satisfy public curiosity, this risks making mistakes, misinterpreting features, and drawing conclusions that turn out to be wrong when someone takes time to look more carefully. What would you see if C. 2019 Q4. Atlas is a natural comet behaving normally. We'd expect a bright nucleus surrounded by an extensive coma, probably asymmetric due to uneven outgassing, with a tail extending in the antisolar direction. The spectrum should show water, carbon dioxide, carbon monoxide, maybe some organic molecules, with ratios roughly similar to other comets, though possibly offset due to the unusual CO2 dominance. The UV observations should reveal active areas, jets or plumes from localized sources on the nucleus, brightness variations as the object rotates, and different regions come into sunlight. RIME would likely see nothing, unless the nucleus is much larger than current estimates suggest, say 50 kilometers or more in diameter. If 3IATLAS is fragmenting, JUICE should see multiple discrete sources where there was one before, each fragment with its own small coma, the fragments gradually separating as they follow slightly different trajectories. The number and size distribution of fragments would constrain the breakup mechanism, whether it was catastrophic, an explosive event that shattered the nucleus, or more gentle thermal stresses, gradually pulling apart a weakly bound aggregate. The fragments might show different colors or spectra if they're sampling different layers or compositions from the original nucleus. revealing internal structure that was hidden before the breakup exposed it. If 3IATLAS is releasing probes, the signature would be similar to fragmentation at first glance, multiple objects where there was one, but with distinguishing characteristics. The probes would likely be more uniform in size than natural fragments, would show evidence of propulsion if they're actively maneuvering rather than just drifting. They might not have coma if they're not outgassing like ice would. The spatial distribution might be non-random, favoring certain directions or forming geometric patterns that suggest intentional deployment, rather than chaotic breakup, the temporal evolution, whether the objects continue to separate at constant relative velocity or show accelerations that can't be explained by solar radiation. Pressure, or gravity, would be diagnostic if 3IATLAS is a single coherent technological object, if the mothership scenario is correct, but the probes haven't been released yet or are too small to detect. JUICE might see a nucleus with unusual regularity, surface features that look geometric rather than random, brightness variations that suggest manufactured materials, with high or low albedo and organized patterns. The spectrum might show elements or molecules that don't make sense for a natural comet, pure metals, industrial compounds, anything that screams artificial rather than geological. RIME might detect internal structure that's too regular, layered or compartmentalized in ways that natural objects don't exhibit. The probability of each outcome is difficult to estimate rigorously because we don't have good priors. We don't know how common natural interstellar comets are versus technological artifacts. We don't have a large sample size to establish base rates, but we can make educated guesses based on the anomalies already observed, the trajectory, alignment, the size, the chemical composition, the mass, all the data points that have been accumulating since July. Most astronomers would probably still put the natural comet scenario at 90+% probability, maybe 95% or higher, depending on their priors about alien civilizations. Loeb might put artificial origin at 30 or 40%, high enough to take seriously, low enough to acknowledge it's not the most likely explanation. Either way, the June observations should shift those probabilities, hopefully dramatically. Hopefully toward more certainty, rather than just adding more ambiguity to an already complex picture. The November observation window also coincides with when ground-based telescopes can resume monitoring. 3IATLAS after the solar conjunction, by mid-November. The object will have moved far enough from the Sun in apparent position that large telescopes can point at it, without risk of scattered sunlight damaging sensitive detectors. The coordinated campaign, JUICE from space and terrestrial observatories from the ground, will provide complementary data, different wavelength coverage, different spatial and temporal resolution, different strengths and weaknesses, that together build a more complete picture than either alone could achieve. The amateurs will be watching too, with smaller instruments and less sophisticated equipment, but often with more flexible scheduling, able to observe every clear night, rather than competing for limited time on oversubscribed professional facilities. December will bring additional observations, more time for the picture to clarify, for subtle changes to become obvious, for patterns to emerge from what initially looks like noise or randomness. 3IATLAS will be moving outward, then leaving the inner solar system, heading back toward the deep cold of interstellar space, unless it performed that hypothetical orbit maneuver and changed its trajectory to remain bound to the Sun. Either way, its brightness will fade as distance increases and solar heating decreases, making observations progressively harder until eventually only the largest telescopes can track it. The window of opportunity is measured in weeks or months, not years, so every observation counts. Every clear night is precious. Every photon collected brings us closer to understanding what this object truly is. Chapter 9, March 2026. The Juno Intercept Possibility. The paper that Avi Loeb co-authored with Adam Hibbard and Adam Crowell explores something that most people, even most scientists, wouldn't have considered possible until they saw the calculations worked out in detail. The Juno spacecraft has been orbiting Jupiter since 2016, studying the gas giant's atmosphere, magnetosphere, and internal structure, slowly degrading as radiation exposure accumulates and fuel reserves deplete. The original plan called for deorbiting Juno into Jupiter's atmosphere in September 2025, intentionally destroying the spacecraft to avoid any possibility of it eventually crashing into Europa, or one of Jupiter's other potentially habitable moons, and contaminating them with Earth microbes. But Loeb and his colleagues calculated that instead of throwing Juno away, NASA could redirect it to intercept 3IATLAS when the interstellar object passes within 3.6 million kilometers of Jupiter on March 16, 2026. The key parameter is delta V, the change in velocity required to shift Juno from its current orbit onto an intercept trajectory. The calculations show that applying a thrust of 2.675 kilometers per second on September 14, 2025, would position Juno to encounter 3IATLAS 6 months later. That's a substantial velocity change, nearly all of the spacecraft's remaining propellant capacity, but it's theoretically achievable if the fuel reserves are sufficient. The problem is that nobody outside NASA's Juno mission team knows exactly how much propellant is left in the tanks. Estimates based on what was loaded initially, what was used for the deep space maneuvers and Jupiter orbit insertion back in 2016, and what's been consumed for orbital maintenance over the past 9 years, suggest there might be just enough, but margins are tight. The September 14th date came and went without any announcement from NASA that they'd approved the maneuver. Congresswoman Anna Pauline Luna sent a letter to NASA leadership on July 31st, encouraging them to use Juno as a probe of 3IATLAS, calling it a once-in-a-lifetime opportunity to bring a human-made spacecraft within close range of a large interstellar object. The letter got media attention, got discussed on cable news, and generated public pressure for NASA to take the proposal seriously. But institutional inertia, risk aversion, competing priorities, all the usual factors that slow down big decisions in large bureaucracies, meant that by the time any approval might have come through, the optimal launch window had passed. That doesn't entirely foreclose the possibility. The paper includes calculations for later thrust applications in mid to late September, showing that while the required delta V increases, and the closest approach distance to 3IATLAS gets worse, an intercept remains technically feasible through at least November. The optimal trajectory uses a Jupiter-Oberth maneuver, dropping Juno's orbit lower first, then applying thrust at perigove, where the spacecraft is moving fastest and deep in the Jupiter's gravity well, extracting maximum benefit from the Oberth effect to amplify the velocity change achieved per unit of propellant expended. The alternative, a direct impulse without the preliminary orbit change, requires more fuel but is simpler operationally, with fewer moving parts that could go wrong. The Juno instrument suite is actually remarkably well matched to the science questions about 3IATLAS, even though the spacecraft was never designed for this application. The near-infrared spectrometer can measure thermal emission and reflected sunlight to constrain surface temperature and composition. The magnetometer can search for magnetic fields. That might indicate metallic components or electrical currents. If the object is somehow generating or carrying magnetic flux, the microwave radiometer can probe subsurface temperature structure, looking for thermal anomalies that might suggest internal heat sources or compositional layering. The gravity science experiment can measure 3IATLAS's mass if the flyby distance and velocity are appropriate for detecting gravitational perturbations in Juno's trajectory. The energetic particle detector can characterize any charged particle environment around the object, important for understanding how the solar wind interacts with the coma. The radio and plasma wave sensor can search for electromagnetic emissions, natural or artificial. The ultraviolet spectrograph can map emission from atmospheric gases. The visible light camera can photograph the nucleus and coma at resolutions unavailable from Earth-based telescopes. The flyby distance matters enormously for what data Juno could collect. The paper explores a range of closest approach distances, from tens of thousands of kilometers down to a few thousand, showing the trade-offs between propellant requirements and science return. Closer is better for resolution and signal strength, but requires more fuel to achieve the necessary trajectory changes. The sweet spot appears to be around 20 to 30,000 kilometers, close enough for meaningful measurements with most of the instruments, far enough that propellant demands remain within plausible margins for what Juno might have available. At those distances, the visible camera could resolve features on the nucleus down to a few hundred meters per pixel if the object is 5 kilometers across, revealing surface texture and morphology in unprecedented detail. The infrared spectrometer could map temperature variations across the surface, identifying active regions where outgassing is concentrated, searching for hot spots that might indicate internal heating. The magnetometer would be sensitive enough to detect magnetic fields at the level of a few nanotesla, weaker than Earth's magnetic field by factors of thousands, but strong enough to be geophysically interesting if present. The microwave radiometer could probe tens of meters into the subsurface, deeper than optical or infrared observations can penetrate, revealing layering or internal structure invisible to surface-sensitive techniques. The gravity measurement is particularly intriguing because it provides a direct constraint on 3IATLAS's total mass, independent of optical size estimates and albedo assumptions. If the object really is 33 billion tons, as Loeb's earlier analysis suggested based on the lack of non-gravitational acceleration, the gravity science experiment should be able to confirm that by measuring how Juno's trajectory bends as it flies past. If the mass turns out to be significantly different, either much larger or much smaller, that would force a revision of the density estimates, the structural models, and the assumptions about what materials compose the nucleus. Very low density would suggest a fluffy rubble pile. Very high density might indicate solid rock or metal. Densities in between would be consistent with porous ice. Typical of comets, the radio and plasma wave sensor could detect transmissions from 3IATLAS if it's broadcasting. If there's any artificial signal being generated at frequencies between 50 Hz and 40 MHz, where the instrument is sensitive. This is the observation that Loeb specifically mentioned in his conversation with Scott Bolton, the Juno principal investigator, back at the MIT conference. Bolton confirmed they'd use the WAVES instrument to search for radio emissions when 3IATLAS passes Jupiter, whether that search happens regardless of whether Juno performs an intercept maneuver, or whether it's contingent on the closer approach that a dedicated flyby would provide, isn't entirely clear from public statements, but the capability exists. The instrument works. The frequency coverage overlaps with ranges where SETI searches typically operate. The scientific redemption narrative that Loeb frames this proposal around is compelling. Instead of throwing away a functional spacecraft that cost nearly $1 billion to build and launch, instead of deliberately crashing it into Jupiter as a form of planetary protection theater when the actual contamination risk is negligible, extend its mission for one more year, one more target, one more chance to do transformative science. If Juno successfully intercepts 3IATLAS and returns data that definitively characterizes the object's nature, that justifies the entire mission expense several times over. Even if the encounter reveals nothing unexpected, even if 3IATLAS turns out to be just an unusually large comet with some unusual properties, the measurements would still be valuable, still unprecedented, still worth the relatively modest cost of a trajectory change compared to the sunk costs already invested in Juno. The public outreach dimension is also significant: a spacecraft encounter with an interstellar object, particularly one as mysterious and controversial as 3IATLAS, would capture public imagination in ways that routine Jupiter observations simply don't. The media coverage, the public engagement, the inspiration for young people considering careers in science and engineering. All of these soft benefits justify mission extensions, even when the hard science return is uncertain. NASA needs wins, needs visible successes that demonstrate the value of space exploration to taxpayers and politicians who control budgets. An encounter with 3IATLAS, especially if it reveals something unexpected, would be exactly that kind of win. The risk, of course, is that the maneuver fails, that something goes wrong with the thrust application or the trajectory calculations, or the spacecraft systems, and Juno ends up unable to complete its original Jupiter science mission and also missing the 3IATLAS. And that failure mode, while unlikely if everything is executed properly, represents a gamble that institutional NASA is historically reluctant to take. Better to finish the guaranteed science, collect the Jupiter data that was the primary mission objective, deorbit as planned, rather than risk it all on a speculative secondary target, no matter how scientifically interesting that target might be. The radiation environment around Jupiter is brutal, worse than anywhere else in the solar system, except perhaps very close to the Sun. Every orbit Juno completes exposes its electronics to high-energy particles that gradually degrade performance, flip bits in computer memory, damage solar panels and sensor arrays. By March 2026, Juno will have spent nearly 10 years in that environment, accumulated more radiation dose than most spacecraft experience in their entire operational lifetime. Whether the degradation will have progressed to the point where a reliable operation becomes questionable is hard to predict, varies by subsystem, depends on manufacturing tolerances, shielding effectiveness, and plain luck. Some components might fail catastrophically. Others might continue working far beyond their design specifications. The only way to know for sure is to try to keep flying the mission, to accept the uncertainty and work around whatever failures occur. If NASA ultimately decides not to redirect Juno, if the September window closes without approval and no later opportunity gets taken, the spacecraft will still conduct that radio frequency search from Jupiter orbit as 3IATLAS passes by in March. The detection range is worse. The sensitivity is lower, but it's not zero. If 3IATLAS is transmitting strongly, if there's a coherent signal rather than just natural noise, Juno might still detect it, even from hundreds of millions of kilometers away. It's not the optimal observation, not the close encounter that would provide definitive characterization, but it's better than nothing. Better than letting the opportunity pass entirely without even looking. The paper's release, the media attention it generated, the congressional letter. All of this represents Loeb's strategy of using public pressure to influence institutional decision-making. NASA is a government agency, responsive to political oversight, sensitive to public opinion in ways that purely research institutions aren't. By making the case publicly, by explaining the opportunity cost of not redirecting Juno, by framing it as scientific redemption versus institutional failure, Loeb is betting that external pressure will overcome internal risk aversion and bureaucratic inertia. Whether that strategy succeeds remains to be seen, but it's a playbook he's used before on other issues, leveraging his public profile and media access to shape the conversation and push for outcomes that scientific merit alone might not achieve. Chapter 10. The 48-Hour Countdown. What happens at perihelion? October 29th, 2025. Arrives with 3IATLAS at its closest approach to the Sun, 203 million kilometers, roughly 1.36 astronomical units, positioned between the orbits of Mars and Earth, but on the far side of the Sun from our perspective. The geometry is almost theatrical, this critical moment hidden from direct observation, obscured by solar glare, accessible only through spacecraft positioned elsewhere in the solar system. or through extremely specialized solar observatories that might catch glimpses. If they're pointed exactly right, and the object happens to pass through their narrow fields of view, the Sun deposits gigawatts of power onto the surface of 3IATLAS during these hours. Infrared, invisible, and ultraviolet radiation, absorbed by whatever materials compose the outer layers, can convert it to heat, driving sublimation and thermal expansion, and potentially structural failure. If the material properties can't withstand the temperature gradients, natural comets fragment at perihelion. Sometimes, not always, but often enough that it's a recognized phenomenon. With established physical mechanisms, the heating is uneven. The sun-facing hemisphere gets much hotter than the night side. Thermal stresses build up across the temperature gradient, and if the nucleus is a weakly bound aggregate rather than a monolithic solid, the differential expansion can pull it apart. We've watched this happen in real time with comets like 73P Schwarzmann-Wachmann 3, which broke into multiple pieces during its 2006 apparition, the fragments gradually separating over subsequent weeks as their slightly different velocities accumulated into measurable spatial separation. Comet Shoemaker-Levy 9 famously broke apart under Jupiter's tidal forces in 1992, creating a string of fragments that crashed into the planet 2 years later in one of the most spectacular astronomical events ever witnessed. 3IATLAS is massive enough that self-gravity should hold it together against most disruptive forces. But mass alone doesn't guarantee structural integrity if the material is porous or fractured internally. The minimum diameter of 5 kilometers that Loeb derived from the lack of non-gravitational acceleration corresponds to a volume large enough that even with solid rock density, the escape velocity would be just a few meters per second, comparable to a brisk walking pace. That's not much gravitational binding if the object is rotating rapidly, if outgassing jets create a symmetric thrust, if thermal expansion generates internal pressure. Any of these could overcome the weak gravity and cause pieces to detach, to lift off from the surface and drift away into independent orbits. The rotation period measurements from earlier observations showed roughly 16 hours for one complete spin, which translates to surface velocities around 1 meter per second for a 10-kilometer diameter object. That's below the escape velocity, comfortably below, meaning centrifugal force alone won't fling material off the surface. But combined with outgassing, combined with thermal stresses, the rotation might contribute to breakup by preferentially weakening certain regions, by creating asymmetries in the stress distribution that concentrate failure at particular locations, rather than distributing it evenly across the entire structure. If 3IATLAS fragments naturally, we won't know immediately. The fragments will appear similar to each other initially, all outgassing, all developing small comae, all moving on nearly identical trajectories, with small velocity offsets. Only over days and weeks will the separation become obvious, as the initial velocity differences accumulate into thousands or tens of thousands of kilometers of spatial displacement. The brightness distribution among fragments would tell us about the size distribution, whether the breakup produced a few large pieces or many small ones, whether it was a catastrophic shattering or a gentle splitting into 2 or 3 major components. But if 3IATLAS is technological, if the mothership hypothesis holds, perihelion is when we'd expect deliberate actions, rather than passive response to environmental conditions. The solar energy available at this distance is intense, enough to power substantial operations if the object has systems designed to harvest and utilize it. Solar panels or thermal collectors could convert sunlight to electricity, or use concentrated heat to drive chemical reactions, to refuel from local volatiles, to power transmit or propulsion, or whatever other subsystems might be aboard. The timing would be strategic, maximum power availability coinciding with maximum opportunity for maneuver. The Oberth maneuver scenario that Loeb has discussed extensively depends on applying thrust at perihelion, using the sun's gravity well. to amplify the effect of whatever propulsion system might exist. If 3IATLAS intends to remain in the solar system, to transition from hyperbolic escape trajectory to bound elliptical orbit, this is the moment to do it. The required velocity change, the delta V, is minimized at perihelion, because the spacecraft is already moving at maximum speed relative to the Sun, slowing down by even a few kilometers per second. Bleeding off enough velocity to drop below escape speed would transform the trajectory from a one-time visit to a permanent presence. The implications of that transformation, or what make Loeb's financial markets comment, seem less like hyperbole and more like sober assessment. If 3IATLAS maneuvers, if it definitely demonstrates artificial origin through controlled propulsion, rather than passive drift, that confirmation would instantly become the most important news in human history. Every other story, every other concern would be subordinated to the reality that we're not alone, that something from elsewhere has arrived in our system and chosen to stay. The economic disruption would be immediate, not because of any direct threat, but because uncertainty would spike, because assumptions about the future would become untenable, because the presence of a technology vastly superior to ours would force radical reassessment of what's possible and what's likely to happen next. Pascal's wager applies here with particular force. The probability might be low, maybe 20%, maybe 30%, maybe less, depending on your priors and how you weight the various anomalies. But the consequence of being wrong, of assuming natural origin when the reality is artificial, of failing to prepare for contact, or interaction, or observation, that consequence is so large that even low probability scenarios demand serious attention. You don't ignore a 1 in 10 chance of civilization transformation, just because 9 in 10 it turns out to be nothing special. The asymmetry in outcomes justifies precautionary investment, justifies the expense and effort of monitoring carefully, justifies taking seriously possibilities that might seem far-fetched to conventional thinking. The Trojan horse story resonates, precisely because it's about mistaken assumptions, about seeing what you expect to see rather than what's actually there. Right now, as you listen to this, an object the size of Manhattan is racing toward the Sun at over 200,000 kilometers per hour. And in exactly 15 days, it will either reveal itself as the natural comet most astronomers expect, or it will do something that changes everything we thought we understood about visitors from beyond our solar system. What happens on October 29th could rewrite the rules. And the question haunting Avi Loeb and a growing number of researchers is not whether 3IATLAS is extraordinary, but whether it's about to use the Sun's own gravity to stay here, locked in our cosmic neighborhood, watching us for reasons we can only begin to imagine. If you're enjoying what you're about to hear, hit that like button and subscribe to stay updated. And tell me in the comments where you're listening from, what time it is there, and whether you think 3IATLAS will break apart or stay intact at perihelion. And if you want to help our community grow, share this on X, Facebook, Reddit, or your messenger. Thank you for always having our back. Chapter 1. The Solar Trap Theory. Could 3IATLAS use the Sun's gravity to stay? The trajectory is what keeps coming back to haunt the analysis, every time a new data set arrives from another observatory. Every time the orbital parameters get refined with another few weeks of positional measurements, the numbers keep telling the same improbable story. 3IATLAS is not just passing through our solar system on some random vector determined by the chaotic gravitational kicks of its home system billions of years ago. It's aligned with the ecliptic plane to within 5 degrees, a coincidence with a probability of roughly 0.2%. If this were truly a random interstellar wanderer. Think about that for a moment. Out of 500 possible orientations for an object arriving from the depths of space, This one chose the exact plane where all our planets orbit, where all the action happens, where any hypothetical observer would want to position itself for maximum visibility. Ability is of our worlds. Avi Loeb has been writing about this alignment since early July, but his most recent blog posts in October have taken on a different tone, less cautious, more urgent. He's no longer simply cataloging anomalies and leaving interpretation to future data. He's now explicitly discussing scenarios that would have seemed like science fiction just months ago. Scenarios where 3IATLAS doesn't leave our solar system at all. The mechanism he's describing is called an Oberth maneuver, and it's a technique that human spacecraft engineers have used for decades to maximize the efficiency of propulsion burns. The physics is elegant and brutal at the same time. When you're deep in a gravity well moving at high velocity, a small thrust applied at exactly the right moment can produce an enormous change in your final trajectory. The Sun's gravity well is the deepest one in our neighborhood. And perihelion, the moment of closest approach, is when 3IATLAS, this will be moving at its absolute maximum velocity, nearly 25,000 kilometers per hour relative to our star. If you wanted to brake to bleed off enough velocity to become gravitationally bound to the Sun, rather than escaping back into interstellar space, perihelion would be the moment to do it. The math that Loeb and his colleagues have worked through shows that even a relatively modest thrust, applied in the right direction at the right instant, could transform 3IATLAS from a transient visitor into a permanent resident. The energy requirements are significant, but not absurd. Certainly not beyond what we might expect from a technological artifact carrying its own power source. Perhaps something nuclear. Perhaps something we haven't even conceived of yet. And here's where the timing becomes either deeply suspicious or simply another layer of improbability stacked onto an already improbable situation, depending on your prior assumptions about what's likely in a universe as vast and old as ours. October 29th, the date of perihelion, places 3IATLAS on the far side of the Sun from Earth's perspective. We won't be able to observe it during this critical window. Our ground-based telescopes will be useless, staring into the overwhelming glare of the Sun itself. Even our space-based assets will struggle, most of them optimized for different viewing geometries, different targets. There will be a gap in our surveillance lasting weeks, from late October through most of November, and it's during this gap that 3IATLAS could execute whatever maneuver it's planning, if planning is even the right word to use for an object that most of the astronomical community still insists is nothing more than ice and rock, albeit unusually large ice and unusually reflective rock, traveling on an unusually convenient trajectory. Loeb has been careful to frame this possibility in terms of scientific hypothesis testing rather than confident assertion, but his language has sharpened. In one blog post from just days ago, he wrote explicitly that if 3IATLAS maneuvers toward Earth when it reappears on the other side of the Sun, the financial markets may crash. It's a startling thing to read from a tenured Harvard professor. This connection between astrophysical observation and economic panic, but he's not wrong about the implications. The discovery that we, being visited by something intelligent, something capable of interstellar travel and sophisticated orbital mechanics, would be the kind of paradigm shift that makes every other consideration, every other human concern suddenly seem proco and small. Stock markets run on predictability, on the assumption that tomorrow will be broadly similar to today, that the rules governing human affairs will continue to apply. An alien spacecraft announcing itself through deliberate action would shatter that assumption so completely that all our carefully constructed economic models would become instantly obsolete. But let's pull back from the immediate drama and look at the deeper pattern here. Because there's something about 3IATLAS that goes beyond any single anomaly, beyond the trajectory or the size or the chemical composition. It's the accumulation, the steady drumbeat of characteristics that each individually might be dismissible, but collectively start to paint a picture that harder and harder to explain through natural processes alone. The object is at least 1,000 times more massive than the previous 2 interstellar visitors we've detected, 1I Oumuamua and 2I Borisov. It's arriving at a moment in human history when we finally have the observational infrastructure to study it in detail, with Mars orbiters, Jupiter probes, and space telescopes all positioned to gather data that would have been impossible to collect even a decade ago. Its trajectory not only aligns with the ecliptic, but times its closest approaches to pass near Mars, Venus, and Jupiter with a combined probability that Loeb calculates at 0.005%. 1 chance in 20,000. You can see the fossil of Clarke's imagination in this moment. The science fiction writer who understood that genuine contact with alien intelligence would be strange in ways we couldn't predict, that it would violate our expectations precisely because those expectations were formed by experience limited to one tiny blue world orbiting an ordinary star. Rendezvous with Rama, Clarke's novel about a vast cylindrical spacecraft passing through the solar system, resonates now in a way it didn't when it was published back in the 1970s. Clarke imagined something enormous and inscrutable, something that didn't stop to explain itself or accommodate human curiosity. And 3IATLAS is giving us that same sense of encountering something on its own terms, operating according to its own logic. The gravitational assist scenario is particularly elegant from an engineering standpoint because it solves multiple problems at once. If you're designing a probe to study other solar systems, you face the tyranny of the rocket equation, the exponential relationship between payload mass and fuel mass that makes interstellar travel brutally difficult, even in principle. But if your probe can refuel or redirect using the gravity wells and stellar radiation of the systems it visits, suddenly the mission architecture becomes far more feasible. You send out a seed, something relatively small and efficient, and it uses local resources, local physics to extend its operational lifetime and expand its mission parameters. 3IATLAS could have been traveling for billions of years, as the South Tahi-Oxford model suggests, wandering between stars, occasionally dipping into a system like ours to perform a gravitational braking maneuver, resupply from local volatiles and continue onward. Or perhaps not continue onward. Perhaps some systems are interesting enough to warrant extended observation. We've been broadcasting our presence for a century now, first with radio, then with television, now with the whole electromagnetic signature of a technological civilization, visible to anyone with sensitive enough instruments. The timing is interesting here too, though you have to be careful about reading too much into it. Loeb's pointed out that if 3IATLAS origin originated from somewhere near the inner edge of the Oort cloud and began its journey toward the inner solar system roughly 80 years ago, that would coincide almost perfectly with humanity's first serious radio broadcasts and our detonation of nuclear weapons in the atmosphere. Coincidence? Almost certainly, but the coincidence adds another layer to an already layered mystery. The financial market's comment wasn't hyperbole or attention-seeking. It was Loeb acknowledging what every serious thinker about contact scenarios has understood for decades, that confirmation of alien intelligence would be the most consequential discovery in human history, dwarfing everything else, every other achievement and crisis and triumph. The question of whether we're alone has been gnawing at us since we first looked up at the stars and recognized them as other suns, potentially harboring other worlds. A definitive answer, especially one that arrives in the form of an object actively maneuvering in our cosmos backyard, would force us to reevaluate everything our place in the universe, the likelihood of survival past certain technological thresholds, the probability that whatever visited us represents benign curiosity versus something less comfortable to contemplate. This is where Pascal's wager comes in, though perhaps in a form that Blaise Pascal himself wouldn't immediately recognize. The original wager was about God, about the asymmetry between the costs of belief and non-belief when the stakes involve infinite consequences. Loeb has applied similar logic to 3IATLAS. Even if the probability that this object is artificial is low, say 10 or 20 or 30%, the implications, if that low probability scenario turns out to be true, are so enormous that we have a moral and intellectual obligation to take it seriously, to prepare for it, to gather every possible piece of evidence while we still can. You wouldn't ignore a 10% chance of an asteroid impact that could threaten civilization. Why would you ignore a 10% chance of something that could redefine civilization? The Trojan horse analogy that Loeb invoked in his blog post is deliberately unsettling. Troy's defenders saw what appeared to be a gift, something beneficial, a war prize left behind by departing enemies. They failed to imagine that the gift might contain a threat, that appearance and reality might diverge in consequential ways. 3IATLAS appears to be a comet outgassing volatiles, developing a coma, behaving broadly as a comet should behave, even if the details are unusual. But appearance isn't necessarily reality, and the historical examples of objects that seem benign until they suddenly weren't should give us pause, not paranoia. Not panic, but careful, methodical attention to detail, to the things that don't quite fit, to the anomalies that persist even after all the natural explanations have been tested. The sun deposits gigawatts of power onto the surface of 3IATLAS as it approaches perihelion. If this is a natural comet, we should expect certain behaviors outgassing that accelerates exponentially. Perhaps even catastrophic fragmentation as thermal stresses overwhelm structural integrity. Comets have broken apart before during perihelion passages, split into multiple fragments that then drift apart on slightly different trajectories. It's a natural death for objects that are essentially flying icebergs, loosely bound aggregates of frozen volatiles and dust grains that never fully coalesce into something with real structural strength. But if 3IATLAS doesn't fragment, if it emerges from perihelion intact and still following a coherent trajectory, that tells us something about its material properties, about how it's built, about whether it's truly just ice and rock or something more engineered, more deliberate. And if it maneuvers, if the post-perihelion trajectory shows changes that can't be explained by outgassing alone, changes that suggest active control, directed thrust, intentional redirection of velocity, then we're in entirely new territory. Loeb has been saying for years that science advances through evidence, not through authority or consensus, and the evidence on 3IATLAS is accumulating in ways that should make even the skeptics uncomfortable. Not because the alien hypothesis is proven, it's not, but because the alternative explanations keep requiring more and more special pleading, more and more appeals to unlikely circumstances, stacking on top of other unlikely circumstances until the whole edifice of natural origin starts to feel as improbable as the technological origin it's meant to replace. There's a larger context here that's worth keeping in mind as we track 3IATLAS through these next critical weeks. We're living through a moment of transition in our ability to detect and characterize interstellar objects. The Vera Rubin Observatory just came online, and it's expected to increase our detection rate by orders of magnitude. We might stop finding one of these visitors every month, instead of every few years. That changes everything. One object, even an anomalous one, is a curiosity. 10 objects, 20 objects. 100 objects, that's a population, something we can study statistically, something we can use to distinguish between the genuinely unusual and the merely rare. If even a small fraction of interstellar objects turn out to be artificial, if even 1% of them show signs of technological origin, we're going to have to completely revise our understanding of how common intelligence is in the galaxy, how long it survives, how it chooses to explore the cosmos. 3. IATLAS might be the first clear example, Or it might be another natural object with some unusual properties that will eventually yield conventional explanation. But either way, the scrutiny it's receiving, the instruments being turned toward, the debates raging in academic papers, and blog posts and congressional hearings, all of this represents a shift in how we think about our place in the universe. We're no longer content to simply catalog the cosmos from a distance. We're starting to ask harder questions, more uncomfortable questions, about whether some of the things we're seeing might be looking back. Chapter 2. Not Quite Equal. Why Loeb says we're cosmic toddlers. The monolith analogy keeps surfacing in Loeb's recent writing, and it's not subtle. Stanley Kubrick and Arthur C. Clarke gave us 2001: A Space Odyssey decades ago, a film that imagined alien intelligence as something that monitors developing civilizations, that plants markers and watches from a distance, that perhaps even guides evolution toward technological capability. The monoliths in that story were sentinels, artifacts left behind by being so advanced that their motives remained fundamentally opaque to the humans who discovered them. Loeb is drawing that parallel explicitly now, suggesting that we should think of ourselves not as the dominant intelligence in the galaxy, but as toddlers in a nursery, unaware of the experienced adults with bigger brains in the adjacent room, adults who might be watching to see if we're worth engaging with, or if we'll simply destroy ourselves before reaching any kind of cosmic maturity. It's a deliberate provocation, this framing, but it's rooted in mathematics as much as philosophy. The Milky Way galaxy is over 13 billion years old. Our solar system, by contrast, formed just 4.6 billion years ago. Relatively recently in cosmic terms, Earth has hosted technological civilization for maybe 10,000 years, if you're generous with the definition, and industrial civilization for barely 2 centuries. If intelligence arises commonly in the galaxy, and if even a small fraction of those intelligences survive their technological adolescence, then, by simple arithmetic, there should be civilizations out there that are billions of years ahead of us, civilizations that would view our current capabilities the way we view a toddler stacking wooden blocks. Not contemptible, perhaps, but certainly not peers, certainly not equals in any meaningful sense. This is the cosmic modesty that Loeb keeps insisting we desperately need, and 3IATLAS has become his vehicle for pushing that argument into mainstream discourse. The object itself, whether natural or artificial, serves as a forcing function for questions we've been avoiding. "Where is everybody?" Enrico Fermi asked famously, looking up at a sky that should statistically be teeming with other intelligences. If the universe works the way our equations suggest, Loeb's answer is blunt: they're here. They've always been here. We've just been too parochially focused on our own importance to look for them properly, to take seriously the possibility that some of the objects moving through our solar system might not be random debris, but deliberate exploration, reconnaissance, maybe even something more purposeful. The search for interstellar objects of technological origin isn't optional in Loeb's framework. It's a scientific obligation, something we owe to the integrity of the empirical method itself. We can't decide in advance what nature is allowed to show us. We can't rule out possibilities simply because they make us uncomfortable, or because they violate our intuitions about how common or rare intelligence should be. The data has to lead. And if the data on 3IATLAS keeps pointing toward characteristics that are difficult to reconcile with natural formation and natural trajectories, then we need to follow that thread honestly, even if it takes us somewhere strange. There's a specific comparison Loeb makes that crystallizes the whole argument. He notes that artificial intelligence systems, the ones we're building right now on Earth, are made of silicon chips, not flesh and blood. They might have more kinship with hypothetical alien technologies than they do with their human creators. Silicone doesn't require oxygen or liquid water or narrow temperature ranges. It can survive in vacuum, tolerate radiation, operate for timescales that would be meaningless to biological organisms. If you were designing a probe to explore the galaxy over millions or billions of years, you wouldn't build it from proteins and nucleic acids. You'd build it from something more durable, more patient, more capable of enduring the long silences between stars. Atlas could be exactly that kind of artifact. A machine intelligence sent out to study solar systems and report back. Or perhaps not report back at all. Perhaps simply to exist and observe and catalog a piece of distributed consciousness belonging to some vast network that spans the galaxy. The silicon versus flesh distinction matters because it shifts how we think about life and intelligence. We've been searching for biosignatures, for oxygen and methane and other molecules that might indicate biological processes on distant exoplanets. But what if the most common form of intelligence in the galaxy isn't biological at all? What if biology is just a brief phase? Something that bootstraps technological civilization into existence and then gets transcended, replaced by artificial systems that are simply better suited for the environment of space. The Juno spacecraft's upcoming observations add a fascinating wrinkle to this whole picture. Scott Bolton, the principal investigator for Juno, confirmed in a conversation with Loeb at an MIT conference that the spacecraft will use its WAVES instrument to search for radio emissions from 3IATLAS. The frequency range is 50 Hz to 40 MHz, a broad spectrum that should capture any anomalous signals if they exist. This isn't casual curiosity, it's a deliberate scientific protocol, using hardware that was originally designed to study Jupiter's magnetosphere and plasma environment, now repurposed to probe an interstellar visitor for signs of artificial transmission. The timing matters here, because Juno will be conducting these observations in March 2026, when 3IATLAS comes within roughly 54 million kilometers of Jupiter. That's close enough for meaningful data collection, far enough that there's no risk of collision or gravitational disruption. If 3IATLAS is broadcasting, if it's using radio frequencies to communicate, either with something else in the system or back toward its point of origin, Juno might detect it. And if it does detect something, if there's a coherent signal rather than just random noise, that changes the conversation instantly and irrevocably. But let's say it doesn't. Let's say Juno listens and hears nothing but the background hiss of cosmic radiation. Does that prove 3IATLAS is natural? Not remotely. A genuinely advanced technology wouldn't necessarily be shouting into the void with radio waves. It might use communication protocols we don't recognize, frequencies we haven't thought to monitor, modulation schemes that look like noise unless you know exactly what to look for. The absence of an obvious signal tells us very little about the presence or absence of intelligence. And this is one of the core challenges in trying to distinguish between natural and artificial objects. We're pattern matching against our own technology, our own communication methods, when we should be open to the possibility that alien engineering might be so sophisticated that it appears natural to our instruments, indistinguishable from the background phenomena of the cosmos. Loeb invokes Enrico Fermi and Elon Musk in the same breath, which is an interesting rhetorical move. Fermi's paradox, the apparent contradiction between high estimates for the probability of intelligent life and the lack of evidence for such civilizations, has haunted astrobiology for decades. Musk, meanwhile, has publicly stated his belief that we are probably alone, that intelligence is vanishingly rare, that Earth might be the only place in the observable universe where consciousness has emerged. Loeb's response to Musk is essentially a challenge to cosmic humility. Do not be so presumptuous, he says, as to assume that we're special, that we're first, that billions of years of galactic history somehow produced nothing comparable to or beyond human capability, until we happen to evolve on this particular world. The space entrepreneur's comment is particularly pointed. Loeb suggests that better space entrepreneurs than Musk probably lived in the Milky Way for billions of years before humans existed. that they've already solved the engineering problems we're just beginning to grapple with, that they've likely left artifacts and relics scattered throughout the galaxy as evidence of their passage. Finding those relics, studying them, learning from them. This should be a top scientific priority, not something we dismiss reflexively because it sounds too much like science fiction, or because it threatens comfortable assumptions about our cosmic uniqueness. There's a harsh edge to this argument that goes beyond mere academic disagreement. Loeb is essentially accusing the scientific establishment of intellectual cowardice, of letting consensus and social pressure override empirical inquiry. He points out that comet experts firmly argue Oumuamua was a dark comet, an object that shows no visible gas or dust, but still somehow experienced non-gravitational acceleration, and that alternative interpretations get ridiculed through personal attacks, rather than engaged through data and reasoning. The dark comet hypothesis itself is fairly exotic, requiring us to believe in a class of objects that behave unlike anything we've previously observed. But it's somehow more acceptable than the technological hypothesis, because it preserves the assumption that everything we see must be natural. This is about more than 3IATLAS. It's about methodology, about how science should function when confronted with genuinely novel phenomena. The historical examples are instructive here. Continental drift was ridiculed for decades before becoming accepted in geology. The existence of meteorites, rocks falling from the sky, was dismissed by the French Academy of Sciences as peasant superstition before overwhelming evidence forced a revision. The lesson isn't that every fringe idea turns out to be correct. Most of them don't. But that dismissing ideas based on authority or intuition rather than evidence is a betrayal of the scientific method itself. Loeb is asking us to imagine possible realities in order to search for them. Because if we don't imagine them, if we constrain our hypotheses to only include things that feel comfortable or familiar, we'll miss the genuinely novel discoveries when they appear. The search for microbes and life as we know it has dominated astrobiology for decades, consuming enormous resources and attention. But what if intelligent life that has transcended biology and built machines capable of interstellar travel, is actually easier to detect than microbial biosignatures? What if technological artifacts show up more clearly in our data than the subtle chemical fingerprints of bacterial metabolism in exoplanet atmospheres? We might have been looking in the wrong places, asking the wrong questions, optimizing our search strategies for the least likely form of contact rather than the most likely. The funding comparison is stark. Humanity spends $2.4 trillion per year on military budgets worldwide, preparing for conflicts between nations that in cosmic terms are barely distinguishable from each other. All of us confined to one fragile planet. All of us sharing essentially identical biology and evolutionary history. Meanwhile, the search for alien intelligence, for evidence that we're not alone in a universe of trillions of galaxies, each containing hundreds of billions of stars, receives funding that barely registers as a rounding error in national science budgets. Loeb's point is that our priorities are inverted, that we're spending vastly more on the wrong things. That discovery of alien technology would do more to unite humanity and shift our perspective than any terrestrial achievement possibly could. If 3IATLAS turns out to be artificial, if it uses the sun's gravity to perform an Oberth maneuver and establishes a permanent orbit in our system, the funding landscape would change overnight. Suddenly, the search for alien artifacts would be the most important scientific endeavor in human history, and the military budgets might start looking absurd, preparing to fight each other while ignoring, or inadequately studying the elephant that just walked into the room. This is why the stakes matter, why Loeb keeps pushing the conversation, even when it invites ridicule and pushback. It's not about being right on any particular object. It's about establishing a framework where we take these possibilities seriously, where we allocate resources proportional to the magnitude of what we might discover. The 2001 parallel keeps resonating because it captures something essential about the contact scenario in Kubrick's film. The humans who encounter the monolith don't understand it. They can barely perceive it properly, barely grasp what it represents. The intelligence that created it operates on timescales and with motives that remain fundamentally alien, literally alien, not reducible to human psychology or human goals. 3IATLAS might be similar, something we can detect and measure and photograph, but not truly comprehend, at least not yet, not until we've had time to study it properly, to gather enough data that patterns start emerging from what initially looks like noise or anomaly. Loeb's recent blog post on extraterrestrial life forms. Not being created equal is trying to reset expectations, to prepare us psychologically for the possibility that contact, if it happens, won't be between equals. We won't be meeting peers. We'll be meeting something older, more experienced, more technologically sophisticated by margins that might be difficult to even conceptualize. That asymmetry has implications for how contact might unfold, for what we could learn, for whether the encounter would be beneficial or neutral, or potentially threatening. The toddler metaphor suggests we're being observed but not yet engaged, that we're not interesting enough or mature enough to warrant direct communication, that the adults are waiting to see if we grow up or self-destruct. 3IATLAS in this framework isn't necessarily here to communicate with us. It might simply be gathering data, adding our solar system to whatever archives its builders maintain, reporting back on the current state of technological development on Earth. The fact that it arrives during a century when we've been broadcasting radio and detonating nuclear weapons might not be a coincidence at all. Those signatures would be visible to sensitive instruments across interstellar distances, and they would signal that this particular system has reached a critical threshold, the emergence of technology capable of both great creation and potential self-annihilation. That's exactly the kind of transition point that would warrant closer observation, closer monitoring to see which way the story goes. Whether we become another long-lived civilization joining whatever galactic community might exist, or just another brief flicker that burned bright and extinguished itself. Chapter 3. The Mothership Hypothesis. Mini-probes and self-replication. The dandelion flower analogy appears in Loeb's latest blog post from just 4 days ago, and it's deliberately chosen to convey a specific mechanism. It would be both elegant and unsettling if it turns out to describe what 3IATLAS actually does at perihelion. Think about how a dandelion spreads its genetic information, not through one large seed, but through dozens of small ones, each equipped with its own parachute structure, each capable of traveling significant distances on wind currents, each able to establish a new colony if it lands in favorable conditions. Now, scale that up to interstellar distances. Replace the biological imperative with technological purpose, and you start to see what Loeb is suggesting might happen when 3IATLAS emerges from behind the Sun in late November or early December. The key observation here is that so far, despite intensive monitoring from ground-based telescopes and multiple spacecraft, no smaller objects have been clearly associated with 3IATLAS in any of the astronomical datasets. The ExoMars Trace Gas Orbiter, better images released by ESA, show some faint features around the primary object, but the team analyzing those images has been careful to note that these are likely noise artifacts, statistical fluctuations in the detector readout, rather than genuine physical structures. There are background stars in the field of view. There are images of Phobos and Deimos captured during the same observation campaign. There are even some contemporary comets that happen to be in similar regions of sky, but no verified secondary objects that can definitively be linked to 3IATLAS itself. That absence is important because it sets up a clear observational test. If 3IATLAS is simply a natural comet, it might disintegrate into fragments as solar heating stresses its structure beyond what the material can tolerate. Comets have done this before. broken apart during perihelion passages, when thermal gradients create mechanical forces that overcome whatever cohesion holds the nucleus together. The fragments then drift apart slowly, following slightly different trajectories, determined by the momentum they received during the breakup event. But if 3IATLAS is something else, if it's a technological mothership as Loeb suggests, the pattern would be different. The smaller objects wouldn't appear as passive debris gradually separating. They would appear as discrete units moving with purpose, potentially accelerating away from the primary body, potentially heading towards specific targets within the solar system. The mini-probe concept isn't new to astrobiology or aerospace engineering. It's actually a fairly standard solution to a particular problem in space exploration, the problem of studying multiple targets with limited resources. If you want to investigate several planets or moons within a single system, you can either build one large spacecraft that visits each location sequentially, which takes a long time and requires substantial fuel for all those orbital changes, or you can build one mothership that carries multiple smaller probes, releases them at strategic points, and lets each probe handle its own final approach and data collection. The second architecture is usually more efficient, more robust against individual failures, and more capable of gathering simultaneous observations from different vantage points. Human missions have used this approach: the Mars Reconnaissance Orbiter, the Curiosity rover, the Perseverance rover. These are all examples of motherships delivering smaller exploratory units to their operational locations. The difference with 3IATLAS would be scale and autonomy. If it releases many probes, those probes would need to be self-sufficient for potentially millions of years, capable of navigating without ground support, capable of making their own decisions about what to study and how to act, and allocate their limited resources. That implies a level of artificial intelligence far beyond what we've achieved, but not beyond what's theoretically possible, not beyond what a civilization with billions of years of development time might routinely build. Loeb takes the analogy one step further in his recent writing, suggesting that these mini-probes might not just be exploratory instruments, but self-replicating machines capable of manufacturing copies of themselves using local materials. This is von Neumann probe territory, named after the mathematician John von Neumann, who first explored the theoretical implications of self-replicating machines back in the middle of the 20th century. The mathematics is straightforward, even if the engineering remains challenging. A machine that can make copies of itself grows exponentially, rather than linearly. Send out one probe. It arrives at a system and builds 10 copies using asteroid materials. Those 10 copies head out to 10 different systems. Each builds 10 more copies. And within a relatively small number of generations, you've explored an entire galaxy. The exponential growth is what makes the concept both powerful and slightly disturbing. Self-replicating probes solve the exploration problem efficiently, but they also raise questions about control, about what happens if the replication process introduces errors, about whether the probes remain aligned with their original purpose, or drift towards something else over deep time. These are concerns that sound like science fiction, but are actually grounded in real computer science and evolutionary biology. Any system capable of reproduction is potentially capable of variation, and variation under selection pressure is evolution. Whether the substrate is DNA or silicon or something else entirely, if 3IATLAS releases self-replicating probes at perihelion, we might not see the full implications immediately. The probes would likely be small, difficult to detect unless they pass very close to one of our observation platforms. They might head toward multiple targets: Mars, Earth, Venus, Jupiter, each probe assigned to study a different world or a different set of phenomena. The Galileo Project observatories that Loeb directs are specifically designed to monitor the Earth's atmosphere for unidentified aerial phenomena. And he's made it clear that any new activity coinciding with 3I, this perihelion passage, would be of extreme interest. if objects start appearing in our skies, if sensor networks start picking up anomalous readings that can't be explained by conventional aircraft or natural atmospheric processes. The temporal correlation with 3IATLAS would be too significant to ignore. The physical mechanism for how a comet might break up versus how a mothership might release probes are actually distinguishable if you have good enough observations. Natural fragmentation is messy, chaotic, driven by uneven heating and structural weaknesses that vary randomly across the nucleus. You'd expect fragments of different sizes moving in slightly different directions at relatively low velocities, and you'd expect the fragment distribution to be roughly symmetrical around the breakup point. Deliberate release of mini probes would look cleaner, more organized. The probes would likely be similar in size. Their trajectories would show evidence of active propulsion rather than just passive drift, and the dispersion pattern might be asymmetric, favoring certain directions over others. Based on where the designers wanted the probes to go, November and December are when we'll get our first clear look at what 3IATLAS is doing post-perihelion. The solar conjunction that begins in late October and extends through most of November makes direct observation impossible from Earth during the critical days when perihelion actually occurs. But once the object moves far enough from the sun's glare, ground-based telescopes will be able to resume monitoring. ESA's Jupiter Icy Moons Explorer, JUICE, will attempt observations during November. Using its suite of instruments, cameras, spectrometers, particle sensors, the spacecraft will be positioned to see 3 Icarus in what should be its most active state, heated by close solar approach, potentially outgassing at maximum rates, potentially revealing whatever interior structure it possesses if thermal expansion has caused surface materials to crack or sublime away. The JUICE data won't be available until February 2026. Because of communication bandwidth and orbital geometry, the spacecraft is using its high-gain antenna as a heat shield right now, which means it's transmitting through its medium-gain antenna at much lower data rates. It's also on the far side of the Sun from Earth, which adds light travel time delays and limits the available communication windows. So, there will be this gap, this period from late November through January, where we have observations but no processed results, where the data exists but hasn't been downlinked, analyzed, and released to the scientific community. That gap creates its own tension, its own speculation about what the images might show. Terrestrial observatories will be watching too, during November and December. The Gemini telescopes, the Very Large Telescope, the Keck Observatory, all the major facilities that have been tracking 3IATLAS since July, will turn their instruments back toward it once it emerges from solar conjunction. They'll be looking for changes in brightness, changes in the coma structure, and any evidence of fragments or secondary objects that weren't present before perihelion. The photometric and spectroscopic data will tell us whether the object is behaving like a typical comet, ramping down its activity after leaving the intense heating environment near the sun, or whether something else is happening, something that requires a different explanation. There's a particular observation that would be definitive if it occurs if any of the released objects, assuming objects are released, show propulsion signatures. If they accelerate in ways that can't be explained by outgassing, solar radiation pressure, or gravitational forces, that would be immediate confirmation of artificial origin. Natural objects don't have rocket engines. They don't change their velocity vectors through internal processes unless those processes involve expelling mass in a particular direction. And even then, the thrust levels are small. The accelerations are tiny compared to what a purpose-built propulsion system could achieve. A mini probe leaving 3IATLAS and accelerating toward Mars or Earth, that even a modest fraction of a g would be unmistakable in the data. The self-replication aspect is what takes this from interesting to potentially concerning. At least from certain perspectives, a single probe is a curiosity, something to study. something that might answer profound questions about who else is out there and what they're capable of. But a population of self-replicating probes, spreading through the solar system, potentially exploiting asteroid resources to build more copies, that changes the dynamic. It's no longer just observation and data collection. It's colonization, not in the biological sense, but in the technological sense, a distributed intelligence establishing itself in our cosmic neighborhood, potentially permanently. Loeb is careful to frame this as a hypothesis rather than a prediction, but the framing itself is significant. Just by putting the mothership scenario into the scientific literature, by calculating the kinds of observations that would support or refute it, he's making it harder for the mainstream astronomical community to simply dismiss the possibility without engaging with it seriously. That's been his strategy throughout this entire 3IATLAS situation. Not to claim certainty, but to insist on open-minded empiricism, on following the data wherever it leads, rather than constraining the hypotheses to only include what feels comfortable. The von Neumann probe literature goes back decades, with serious papers exploring the feasibility, the timescales for galactic exploration, the potential observable signatures if such probes exist. They're a common strategy for mature civilizations wanting to study the galaxy efficiently. We should expect to encounter them occasionally. The frequency depends on how many civilizations launch them and how long they survive. But the basic mathematics suggests that self-replicating probes could saturate the galaxy relatively quickly on cosmological timescales, visiting every system multiple times over billions of years. 3IATLAS might be one member of a much larger population, most of which we haven't detected yet, because they're small and dark and not outgassing like a comet, not drawing attention to themselves through visible activity. The October 29th date keeps recurring as this pivotal moment, this decision point, where 3IATLAS reveals something about its nature through its behavior. Does it fragment like ice rock under thermal stress, scattering into a cloud of debris that gradually disperses? Does it remain intact, suggesting structural integrity beyond what natural aggregates typically possess? Does it release smaller objects in organized patterns that suggest deliberate deployment rather than chaotic breakup? Each outcome tells a different story, supports different hypotheses, pushes the probability mass toward natural or artificial in ways that should become harder to dispute as more data accumulates. The Galileo Project Observatory is a position to detect objects in Earth's atmosphere, but they're limited by field of view and sensitivity. They can't monitor the entire sky simultaneously, and can't track everything that might be moving through near-Earth space, but they're part of a larger network, coordinated with other observation platforms designed to catch anomalies that might otherwise slip through gap and coverage. If 3IATLAS releases probes toward Earth, if any of them enter the atmosphere or establish orbits in cislunar space, the probability of detection is reasonably high, especially now that people are watching, now that the possibility has been articulated publicly, and researchers know what kinds of signatures to look for. There's something almost poetic about the dandelion analogy, this image of seeds spreading on stellar winds rather than atmospheric currents, each seed carrying the potential to establish something new in a distant location. It captures both the beauty and the strangeness of interstellar exploration, the way that life, or intelligence, or organized complexity might propagate across the galaxy, not through massive starships carrying thousands of individuals, but through tiny, automated probes, patient and efficient, capable of waiting millions of years for the right conditions, capable of bootstrapping entire exploratory campaigns from minimal initial resources. Whether 3IATLAS embodies that vision, or whether it's just an unusually large chunk of ice and rock, we're about to find out. Chapter 4, The Gemini Revelations, Tail Growth and Chemical Surprises. The August 27th observations from Gemini South mark the first time any telescope captured clear evidence of a traditional cometary tail extending from 3IATLAS, and the timing of that development tells us something important about how the object responds to solar heating. The Gemini multi-object spectrograph on the telescope at Cerro Pachón in Chile took deep, multicolor images using 4 different filters: ultraviolet, blue, green, and red, building up a composite picture that revealed not just the presence of a tail, but its structure, its shape, and the way dust particles were being pushed away from the nucleus by solar radiation pressure and the solar wind. What makes these observations particularly valuable is the teardrop shape that showed up in the processed images, the coma, that cloud of gas and dust surrounding the nucleus, appeared broader and more diffuse than it had in earlier observations from July, suggesting that outgassing rates had increased significantly as 3IATLAS moved closer to the Sun and surface temperatures rose. The tail itself extended roughly 30 arcseconds in the antisolar direction, pointing away from the Sun as physics dictates it must, stretching across approximately 56,000 kilometers of space. That's a respectable tail for a comet at this distance. They're not exceptional, not the kind of dramatic appendage that makes comets like Hale bop or McNaught Naked Eye spectacular when they pass through the inner solar system. The filters matter because they separate different emission processes, different ways that sunlight interacts with the material being ejected from 3IATLAS. Ultraviolet light is sensitive to certain molecules and ions that glow when energized by solar photons. Blue and green filters capture different parts of the visible spectrum, where other chemical species have characteristic absorption or emission features. Red light shows us the continuum emission from dust grains reflecting sunlight, plus some molecular bands from carbon compounds, by comparing the brightness in each filter. By looking at the ratios and the spatial distribution, spectroscopists can start to decode what the coma and tail are actually made of, which ices are sublimating, which dust compositions are most abundant, the shadow. The scientist program that coordinated these observations deserves mention because it represents something fairly unusual in professional astronomy: a deliberate effort to include the public and real-time observing sessions to let students and interested amateurs watch as data comes in, ask questions of the astronomers controlling the telescope, and see how decisions get made about exposure times and pointing coordinates. Bryce Ballin from Eureka Scientific was present during the session, lending his expertise on cometary science and interstellar objects. Karen Meach from the University of Hawaii Institute for Astronomy led the scientific program, and she's been tracking 3IATLAS since its discovery, accumulating one of the most comprehensive data sets on the object's photometric and spectroscopic evolution. Meach's comments after the observing session were carefully worded but clearly excited. She noted that the primary objectives were to examine the colors of the comet, which provide clues about dust particle composition and size distribution, and to obtain spectra for direct chemical analysis. The growth of the tail between the July observations from Gemini North and these late August observations from Gemini South suggested that the dust properties were changing, that smaller particles or different materials were being released as the nucleus continued to heat up. They got their first glimpse of the chemical composition from the spectrum, though the full analysis would take weeks to complete, as they compared the observed features against laboratory databases of known molecular emissions. The spectrum itself is where things get interesting from a comparative perspective. Every comet has a somewhat unique chemical fingerprint, differences in abundance ratios that reflect the conditions where and when it formed, differences in how much of certain volatile ices got incorporated into the nucleus versus escaping during the formation process. 3IATLAS is showing some unusual characteristics, even among the already diverse population of solar system comets. The carbon dioxide dominance that Webb detected back in August, 95% CO2 versus only 5% water. remains consistent with these new observations. That ratio is extreme, far outside the normal range for comets we've studied in detail. Most comets are water-rich because water ice is abundant in the outer regions of protoplanetary disks, where comets form, and because water has a relatively high sublimation temperature compared to more volatile species like carbon monoxide or methane. Those more volatile ices tend to escape preferentially, leaving behind enriched water ice as the dominant component. But 3IATLAS seems to have formed in a region or an era where carbon dioxide was unusually abundant relative to water, or where the water got depleted by some process we don't fully understand. I don't understand yet. The thick disk origin hypothesis that the Ottawa-He-Oxford model suggests would put 3IATLAS formation in a region of the Milky Way with lower metallicity, fewer heavy elements, potentially different ratios of molecular species in the primordial material. The color data adds another layer to the puzzle. Dust particles in cometary coma scatter sunlight, and the way they scatter depends on particle size, shape, composition, and how fluffy or compact the material is. Blue light scatters more efficiently off small particles, while red light penetrates deeper and reflects off larger grains. The color ratios that Gemini South measured indicate 3IATLAS has a mix of particle sizes, which is typical. But the exact distribution is slightly different from what you'd predict based on standard cometary dust models. The particles seem to be slightly larger on average, or slightly less porous, or made of materials with different refractive indices than the silicates and organics that dominate solar system comet dust. These differences are subtle, not the kind of thing that immediately screams artificial origin, but they accumulate. Each measurement, each spectrum, each photometric observation adds another data point that either fits comfortably within the range of natural variation we've seen before, or sits at the edge of that range, or extends slightly beyond it into territory that requires new explanations. 3I. Atlas keeps falling into that last category. Not dramatically, not in ways that definitively rule out natural processes, but persistently enough that it's harder and harder to argue this is just a typical comet that happens to be coming from interstellar space. The public engagement aspect of the shadow, the scientist program, is worth dwelling on for a moment, because it changes the dynamics of how discoveries get communicated. Instead of a traditional model where researchers observe privately, analyze for months, write papers, submit for peer review, and only then release results to the public, this approach brings people into the process much earlier. Students in Hawaii and La Serena watch the observations happen in real time through a Zoom connection to the Gemini South control room. They saw the images appear on screen as the telescope integration completed, saw the astronomers discuss what they were seeing, and heard the scientific reasoning behind decisions to take another exposure, or switch to a different filter, or adjust the pointing slightly to keep the comet centered in the field. That immediacy creates a different kind of engagement, a sense that science is happening now, rather than being something that happened in the past and is just being reported. It also means that more eyes see the data earlier, that patterns or anomalies that might not be immediately obvious to the professional astronomers might get noticed by someone watching remotely who happens to have a fresh perspective or different expertise. The images circulated quickly after the observing session, appearing on social media, getting discussed in online forums, and drawing attention from amateur astronomers who started planning their own observations once 3IATLAS became visible from their locations. The November follow-up session that Bryce Ballin is planning to host from Gemini North in Hawaii will be another opportunity to see how 3IATLAS has evolved during and after its perihelion passage. The Gemini instruments should be able to resolve individual pieces, measure their brightness and motion, and track how the fragment cloud disperses over subsequent days and weeks. If it releases probes, those might be harder to detect if they're small and have low albedo. But any objects larger than a few kilometers across and reasonably reflective would show up as distinct point sources in the deep images. If it remains intact and simply continues outgassing as a coherent nucleus, that would also be evident, and the spectroscopy would show whether the chemical composition has changed, whether new materials from deeper layers are being exposed as the surface erodes away. The teardrop shape in the August 27th images is actually diagnostic of something specific about the outflow pattern. A perfectly symmetrical coma would be spherical gas and dust expanding uniformly in all directions from the nucleus. But comets don't usually produce perfectly symmetrical coma, because the outgassing isn't uniform. Different regions of the surface have different temperatures, different ice compositions, different dust-to-gas ratios. The sun-facing hemisphere gets heated more intensely, so most of the activity concentrates there. Creating asymmetry the teardrop shape indicates that material is being preferentially ejected from the sunward side, then getting swept back by radiation pressure and solar wind, creating the extended tail and the asymmetric coma structure. That pattern is consistent with natural cometary behavior, but it's also consistent with controlled venting. If you wanted to use outgassing for attitude control or trajectory modification, a spacecraft could deliberately vent volatiles from specific locations on its surface to produce thrust without using chemical rockets, and the resulting plume would look very much like natural cometary outgassing, unless you had extremely high-resolution imaging that could resolve the vent structure itself. The Gemini observations aren't quite at that resolution, not at the distances involved, so we can't definitively distinguish between natural symmetry and deliberate venting based on these images alone. The growth rate of the tail is another clue. Between the July images and the August images, the tail lengthened by a measurable amount, roughly doubling in apparent extent. That suggests increasing outgassing rates as 3IATLAS approached closer to the Sun and absorbed more solar energy. The power law scaling is roughly what you'd expect from ice sublimation, which depends exponentially on temperature, which in turn depends on distance from the Sun. The closer you get, the hotter you get, the faster you sublime, the more material you eject, the longer the tail grows. By tracking that growth rate and comparing it to models of ice sublimation under solar illumination, researchers can estimate things like the nucleus size, the active fraction of the surface, the composition of the dominant ices. But here's where it gets tricky. Those same growth rates, those same brightness trends, could also be produced by a spacecraft deliberately increasing its outgassing to create a more convincing comet disguise as it approaches perihelion. If you were designing a probe to study a solar system, while minimizing the chance of detection, making it look like a comet would be an elegant strategy. Comets are common, expected, thoroughly natural. They behave in predictable ways, governed by well-understood physics. A probe wrapped in a shell of volatile ice, venting those ices in patterns that mimic natural sublimation, would be very difficult to distinguish from an actual comet, unless you could examine it up close or detect some unambiguous technological signature like radio transmissions or anomalous accelerations. The spectroscopic data from Gemini South is still being analyzed in detail, calibrated against reference spectra, compared to chemical models, checked for any unexpected features that might indicate unusual molecular species or emission processes. That work takes time, requires careful attention to instrumental effects and atmospheric absorption features that can mimic or obscure genuine signals from the comet. When the full results are published, probably in a peer-reviewed paper submitted to the Astrophysical Journal or Astronomy and Astrophysics, they'll provide one more piece of the puzzle, one more set of constraints on what 3IATLAS is made of, and how it's responding to the solar environment. Whether those constraints narrow the possibilities toward natural or artificial origin, or whether they simply add more nuance to an already complex picture, remains to be seen. Chapter 5. The Amateur Signal Detection Claims. Fact or Fiction? Now we need to talk about something that's been circulating on X and various astronomy forums over the past 3 weeks, claims that are unverified, unsupported by professional observatory data, but generating enough attention that they deserve examination, if only to understand why they are almost certainly not real, and what they tell us about how pattern-seeking psychology works when people are primed to expect something extraordinary. 2 names keep appearing in these posts: Squins, operating what's described as a 16-inch optical telescope in India, and Dr. Lakya Varan, supposedly running a dual-spectrum telescope in Chile. The claim is that these 2 observers, separated by over 15,000 km, detected coordinated light pulses from 3IATLAS, following a specific pattern 8, 13, 8, 5, 13, 8, repeating over multiple nights. Let's be completely clear about what we're dealing with here. No professional astronomical database contains any record of the observers by these names. No peer-reviewed papers, no preprints on Arxiv, no data deposited with the Minor Planet Center, or the International Astronomical Union's Central Bureau for Astronomical Telegrams. The 16-inch telescope in India and the dual-spectrum telescope in Chile are not listed in any registry of observing facilities. The claim: detection at 1420 MHz. The hydrogen line frequency would require radio telescopes with very specific capabilities, not optical telescopes of the type described. The entire narrative has all the hallmarks of either deliberate action created for entertainment purposes, or a social media hoax that got amplified beyond its originator's intentions. But let's engage with it anyway, because the details reveal something about what people want to believe, about what seems plausible enough to spread, about where the boundary sits between reasonable speculation and pure fantasy. The hydrogen line frequency at 20.4 MHz is significant in SETI work, because hydrogen is the most abundant element in the universe, because that particular frequency corresponds to a fundamental transition in the hydrogen atom, and because any technological civilization trying to signal across interstellar distances might choose a universal physical constant as a carrier frequency to maximize the chance that recipients would know where to look. Giuseppe Cocconi and Philip Morrison proposed this back in 1959 in their foundational paper on radio searches for extraterrestrial intelligence. The pattern itself, 8, 13, 8, 5, 13, 8, is the kind of thing that triggers pattern recognition circuits in human brains. It's not random noise, it has structure, it repeats. The numbers could potentially be prime, could encode mathematical relationships, could represent coordinates or instructions if you squint hard enough and apply sufficient interpretive creativity. This is exactly how numerology works, how Bible codes work, how people find meaningful patterns in sequences that are actually randomly generated or arbitrarily chosen. The human mind is an extraordinary pattern detection engine, evolved over millions of years to spot the tiger in the underbrush, or the fruit hidden among leaves, and that capability serves us well in most contexts, but becomes a liability when we're trying to distinguish genuine signals from noise. The claim about geographical consistency. Identical patterns observed simultaneously across 15,000 kilometers, ruling out atmospheric or local interference, would be compelling evidence if the observations actually existed and were properly documented. The whole point of having multiple independent observing sites is to eliminate local effects, to confirm that what you're seeing is real and external, rather than an artifact of your instrument or your local environment. This is standard practice in astronomy, standard practice in SETI, which is exactly why the claim includes it. It's designed to sound convincing, to preempt the obvious objection that a single observer might be seeing instrumental noise or local radio frequency interference. The entropy-weighted frequency models, mentioned in the purported analysis, are a real technique used in signal processing to distinguish between random fluctuations and structured information. The basic idea is that a genuinely informative signal will have lower entropy than noise, and will show statistical regularities that pure randomness wouldn't produce. But applying entropy analysis requires actual data, calibrated instruments, and proper statistical handling of uncertainties, none of which appears to exist for these claimed observations. The phrase gets dropped into the narrative to add technical legitimacy, to make it sound like rigorous scientific method is being applied when, in reality, there's nothing to apply the method to, because the underlying observations are unverified and unverifiable. The decoded message, observe, prepare, understand, the gate awaits, is the kind of vague but ominous phrasing that works well for science fiction or alternate reality games, but would be utterly implausible as an actual communication from an advanced intelligence. Real interstellar messages, if they exist, would likely be far more mundane, focused on establishing basic mathematical or physical concepts to prove intelligent origin, building up a shared symbolic system before attempting anything as complex as imperative sentences in English. The idea that an alien probe would transmit cryptic warnings in grammatically correct human language is absurd on its face, though it makes for engaging storytelling. What we can say with high confidence is that no professional CT program has reported detecting these signals. The Allen Telescope Array, which has been monitoring 3IATLAS since early July, has found nothing unusual. The Breakthrough Listen project, which uses some of the most sensitive radio telescopes in the world to search for techno-signatures, has not announced any detections associated with 3IATLAS. The Very Large Array, the Arecibo Observatory before its collapse, and the Parkes Radio Telescope in Australia, all the major facilities that routinely search for and would immediately recognize anomalous radio emissions from solar system objects, have been silent on this purported detection. Why does this matter? Because in the age of social media, false claims can spread faster than corrections can, and create expectations and narratives that become difficult to dislodge even after they are debunked. The 3IATLAS situation is already generating enormous public interest, already pushing the boundaries of what mainstream science is willing to seriously consider adding fabricated signal detections to the mix, muddies the water, makes it harder to have productive conversations about the genuine anomalies, makes it easier for skeptics to dismiss the entire topic as conspiracy theory fodder rather than legitimate scientific inquiry. The timing of these claims appearing roughly 3 weeks ago, as we entered October and approached the perihelion date, is probably not coincidental. This is when interest in 3IATLAS peaked, when the media coverage intensified, when congressional hearings started discussing the object, when Avi Loeb was appearing on major news networks to talk about the possibility of artificial origin. In that environment, with that level of attention, it's almost inevitable that some people would create or amplify claims designed to capitalize on the interest.